So here we are assuming that if n is a positive integer greater than or equal to 2, then it doesn't divide 2 to the power of n minus 1. To solve this, we are going to use a proof by, we are going to consider a proof by contradiction. So to do this, we assume n is greater than or equal to 2, but n does divide 2n minus 1. Now, because n is greater than or equal to 2, there exists a prime divisor p, or I'll just say a prime divisor for now, and then what we're going to do is we're going to let p be the lowest prime divisor. Obviously, if it has a prime divisor, there will be some arbitrary number, not arbitrary, but there will be some number that is the lowest prime divisor. Because it divides n, we know that p divides 2 to the n minus 1. Then we let m be the smallest uh, positive integer, satisfying the equation or the property that p divides 2 to the m minus 1. We know this value exists because we know that p divides 2 to the n minus 1. So it'll either have a lower value, m, such that this is satisfied, or this n here will be the lowest value. All right, to continue, we will note that m divides n. And to show this, assume that n equals qm plus r, and 0 is greater than or equal to q, or r, which is strictly less than m. Therefore, we know that 2 to the n minus 1 can actually be written as 2 to the km times 2 to the r minus 1. P divides the value 2 to the m minus 1 by our assumption that m was the smallest value satisfying this equation. So we know that 2 to the m is 1 modulo p. If this is the case, then we also know that since this value here was 1 modulo p, we know that 2 to the n minus 1 will equal 2 to the r minus 1 mod p. However, if this is the case, then he divides 2 to the r minus 1. And we know that this is a contradiction. This is contradiction notation because r was assumed to be less than m. However, m was assumed to be the lowest value, such that p divides 2 to the m minus 1. Therefore, we know that uh, r must equal 0. So if the remainder is 0, that means that m divides n. And then we need to recall that we're outside of the limit now. We're done here. But we need to recall that p was the lowest prime divisor of n. And since p divides 2 to the n minus 1, we know that p and 2 must be coprime. They cannot not be coprime because then that would mean that p equals 2, but that is impossible considering we have assumed p to divide 2 to the n minus 1. Now here I have pasted the Wikipedia definition of Fermat's Whittle theorem, and we know that p and 2 must be coprime. So using this second equivalent statement here, we know that 2 to the power of p minus 1 must be 1 mod p. So we will write that down here. Oh, I'll write it as FLT, Fermat's Whittle theorem. 2 to the p minus 1 is equivalent to 1 mod p. And that implies that p divides 2 to the p minus 1 minus 1. So, since m is the smallest value satisfying p divides 2 to the m minus 1, we know that m must be less than or equal to p minus 1, and then we know that 1 is less than m, which is less than p, and that m divides n. However, p was assumed to be the lowest prime divisor. But m has a smaller prime divisor because it's a value less than p. This contradicts our assumption, which we made way up here. We assumed that p was the lowest prime divisor of n. So we know p is not the smallest prime divisor. And then this is a contradiction. This is how we denote a contradiction. I'll just write that in brackets to make it clear. And then that means, since we have found our contradiction, that n does not divide 2 to the n minus 1. And we are done.